So good afternoon to everyone. Hope you're doing well. Today we're having an exciting talk, and we're excited to listen to Dr. Nick Holschuh. He's an assistant professor of geology at Amherst College, and his talk is titled Notes from the Field, an overview of the motivation for an approach to ice-penetrating radar data collection at Thwaites Glacier from West Antarctica. We're so excited to hear from you, Dr. Holschuh, and thank you so much for your time. Please.
Thank you very much, Josephine. Let me make sure I can figure out how to share my screen properly. Well, thank you very much for having me to talk. When Nikki first asked me to talk about the field season, she said kind of anything would be interesting to hear. We're all kind of interested in hearing about what fieldwork in Antarctica looks like. And so I thought I would share a little bit about the motivation for the field study that I participated in this last year. I was in West Antarctica from many different folks. Only a subset of them are listed here. So I always like to lead off with that. So as I mentioned, the talk is going to be split into two main parts. The first is background, which is really the motivation. Why do we put in all of this energy to get scientists to Thwaites Glacier? And to answer that question, we need to first ask what controls Antarctic mass change. The second half of the talk will be focused on what radar data are, how are they collected, and how specifically did I collect data in West Antarctica this last winter. In a moment, I'm going to start this animation. These are data collected from a satellite that called the GRACE satellite, the Gravity Recovery and Climate Experiment, that measures changes in mass in the Earth system. Basically, the movement of water between Earth's ice sheets and the ocean. The two curves that you see here are the average change in mass for Antarctica in blue and Greenland in orange over the last 20 years. And when I start the animation, instead of looking at the full averages for these two ice sheets, you're going to see how mass change is distributed in space. So areas that are highlighted in red are areas where ice is lost from an ice sheet. Areas in blue are areas where ice is being gained. And so when we look at this 20-year time series, some patterns start to emerge. First off, you'll see that even though the average behavior in Antarctica is ice mass loss, it's not uniformly losing mass everywhere. And in fact, most of the ice mass loss is really concentrated in one particular part of West Antarctica, an area we call the Amundsen Sea embayment. This looks somewhat different from Greenland. Greenland is essentially losing ice uniformly around its margins in the low elevation areas. Whereas if we look across Antarctica, in some of the low elevation areas, like here in East Antarctica, we're actually gaining mass. More ice is being added than is being lost year over year. So there are lots of things we have to consider to explain the patterns we see in Greenland and Antarctica. And in our effort to explain those patterns, we're motivated to go collect data in the field, which I'll talk about in the second half of this talk. One thing that I like to start with when I'm talking about Antarctica specifically is helping us situate it in the climate system. So this is a map of the Earth. It's a satellite image, projection of a satellite image of the Earth. And for those of you who have taken a climate dynamics course or think about global atmospheric circulation, you know that because the sun heats the equator more than it heats the poles, and because the Earth is rotating, we set up this general sense of atmospheric circulation where we have winds that blow from the west to the east in the mid-latitudes. That essentially isolates the poles from the tropics. If you've heard of the jet stream is this jet of air that separates tropical air in the low latitudes from polar air at the high latitudes. In a world where the Earth is just a perfect sphere, then we might expect that the winds go perfectly from west to east, like I've drawn them on here. But those winds actually interact with the continents. In the northern hemisphere, we have these high mountains in the western US, the Rockies and the Coast Ranges. We've got high mountains in Central Europe, in Asia, and those mountains actually cause a deflection of the jet stream as it is transporting air from west to east. So in reality, in the northern hemisphere, we have this really wobbly jet. And when you hear about snowstorms in Texas, a snowstorm in Texas is because the jet has wobbled really far to the south over the United States, bringing that cold polar air with it. Because the northern hemisphere has this really wobbly jet, it actually brings warm air up over Greenland. So during the summer, there are large parts of the year where the air is warm enough to actually melt the ice from above. That is not true in Antarctica. Antarctica, the jet that transports air from west to east, isn't affected by continents because we have this open ocean. So we have this relatively direct pathway for the winds to travel, and it really keeps that cold polar air over the Antarctic continent. So while Greenland is changing in part because of the warm air causing melting at the surface, that is not a major driver of change in Antarctica today. So when we look at mass loss in West Antarctica, like we see at Thwaites Glacier, we need to better understand what's driving it and how that change, whatever the climate change is that drives it, translates to changes in the dynamics of the glaciers there. This is a map on the left of the elevation of the seafloor off the coast of West Antarctica. So in black is the ice sheet over here. The part that's really actively changing is where my mouse is. And you can see offshore, there's a relatively shallow seafloor, the continental shelf. And as you move further offshore, there's this really deep abyssal ocean. And sitting at the bottom of that really deep ocean is actually warm, salty water. We call it circumpolar deep water. And so this map over here, this is another representation of that same area. The color is showing you the temperature of the water sitting just off the seafloor. And so you can see where we're in the deep abyssal ocean, we have this warm ocean water. It turns out that as the planet warms, there are changes to the winds and changes to what we call buoyancy-driven overturning that pump that warm water up against the ice sheet. So over here is an ocean model that I'm going to set in motion. These are tracers that are showing what happens to that deep, circumpolar deep water that's warm after you let the winds pump that water onshore. So as the winds drive circulation over the ocean, that pumps warm water up against the margins of the ice sheet, and that warm water melts the edges. So all of the changes that we're seeing in West Antarctica are really a function of this delivery of warm ocean water up against the margins of the ice sheet. But it wasn't that all of the melting was happening just in this very thin band, or I should say all of the ice loss is happening in the very thin band. This cartoon over here you can think of as a cross-section of a glacier. So here's the ice in white, here is rock underneath in brown, and as that ice floats out towards the ocean, eventually it's thin enough that it's actually floating on top of the seawater. Ice is flowing by the force of gravity. It's flowing from the interior out to the ocean. And that gravitational force is in part balanced by a frictional resistance to flow at the contact between ice and rock. So this rock is really holding the ice back, making it so it doesn't flow too quickly out into the ocean. Well, as you pump warm water up against the margin of the ice sheet, you actually concentrate melt right at that boundary between ice and ocean. And as you melt the ice there, it causes it to thin. When it thins, more of the glacier than there was before starts to go afloat. And as this thinner section of the ice sheet floats, now that frictional resistance to flow goes away. And so this part of the ice sheet accelerates. As it accelerates, the downstream part of the glacier pulls away from the upstream part of the glacier, and thinking about it like taffy or silly putty being stretched, the whole glacier continues to thin. And so as it thins, again, it ungrounds, it goes afloat, it accelerates, it thins. It ungrounds, it accelerates, it thins. It ungrounds, it accelerates and thins. And there's a positive feedback in these specific marine glaciers called the marine ice sheet instability that we think could lead to the loss of all of West Antarctica. So what we see in the thinning pattern here around Thwaites Glacier is a combination of ocean-driven warming, which melts the edges, and the acceleration and enhanced discharge of ice from the interior. So even though the forcing to the system that's coming from the ocean is really just at the edge of the continent, the interior of the ice sheet is responding. Mathieu, as well as working together with some students that are my collaborators at Penn State, have modeled some of the mass loss from West Antarctica. And if you apply a constant ocean forcing to the edge of Thwaites Glacier, we expect that it will unground, thin, retreat, unground, thin, retreat, in a way that's characteristic of this marine ice sheet instability. That process and the rate and magnitude of ice loss for Thwaites Glacier over the next century is a major source of uncertainty in our projections of future sea level rise. So we have the component of the system that's forced by the climate. As the winds change the circulation of the ocean, we thin right at that grounding line. But then we also have the response, the differential acceleration at the margins versus the interior. As the margins accelerate, it causes the ice to stretch and thin, and it causes this positive feedback. But this part, the interior response, that is a product of all kinds of physical processes that are poorly understood. And this differential acceleration, the acceleration near the margins and not so much in the interior, depends on what material the ice is sitting on. Because it turns out the rate, or I should say the response of the glacier inland depends a lot on the interaction between ice and rock, ice and water, ice and disaggregated sediment that sit underneath the glacier. And so if we're going to make predictions about how much and how fast Thwaites Glacier is going to change, we need to know something about what sits underneath the ice sheet. It is a first order control on how the interior responds to ocean warming. So in 2017, the US and the UK jointly decided that sending geophysicists to Thwaites Glacier was one of the top priorities for Antarctic science, because the future of Thwaites and the eventual interior response to ocean forcing depends on all kinds of processes that are poorly studied and poorly understood. So they decided that they would fund folks who would go onto the ice sheet to study these processes playing out at the contact between ice and rock. There are people studying the ocean, people studying the atmosphere, folks improving models of ice flow, all to tell this integrated story of what is happening at Thwaites Glacier. So this is kind of a visual representation of all of the different projects that were funded as part of the International Thwaites Glacier Collaboration. It was a big $25 million initiative with support, like I said, from the US and the UK to bring scientists together to study all of these processes. I was a part of a project that was called GHOST, which was really focused on this interaction between ice and rock. So our goal was to collect data over as much of Thwaites Glacier as is possible to better constrain what are the physical properties underneath the ice and how might those inform our projections of future sea level rise. So that's why we decided to invest a ton of money into studying this glacier, because it is our major source of uncertainty, and it is a glacier the size of Florida that is heterogeneous, and we want to understand that heterogeneity. How do properties vary in space? And to do that, my primary tool is ice penetrating radar. So I always like to give a little bit of a primer on what radar data are, and I think it's particularly useful because there are lots of folks in iHARP who have been thinking about ice penetrating radar data. So you can think about this on the left as a cross-section of a glacier. This gray body on the bottom is rock or sediment or whatever underlies the ice sheet system. This line up here is the top surface of a glacier. And inside you can see all of this layering associated with historical accumulation. If we're sitting here at the surface of the glacier with a radar, what that radar does is it sends out a pulse of light, an electromagnetic wave. And it listens to perturbations of the electromagnetic field through time. Anywhere that wave comes in contact with a contrast in the electrical properties of the system, a reflection is generated. So some amount of that light is reflected back towards the instrument. And when these reflections arrive, we see this little spike in the electromagnetic field. So in principle, what the radar is measuring is just this time series of how much light is being received at any given moment. By collecting that same time series here and here and here and here and here, collecting many of these, we start to get a picture of the geometry of the subsurface. And so instead of, if we represent this as color instead of as wiggles, what we end up with is an image. So this radargram gives us a sense of the structure of the glacier itself and the geometry of the substrate. What does that contact between ice and rock look like? Implicitly assumed in that image that I described below or before is that these reflections are coming from right below our instrument. But the reality is that some of the signal might be coming from the left, some of the signal might be coming from the right. And so when we look at radar data, we have to do some processing to generate an image that is geolocated, that describes where those reflections are arriving in space. Sorry, my Slack notifications keep coming up. So one way that we can do that with radar is through what we would call a real aperture, or an antenna that is not just a point, but it's a line. Because you can imagine, if a wave is coming from the right, and it arrives here first, and then here, and then here, and then here, and then here, we would be able to see that in our data. That it didn't arrive everywhere simultaneously, but arrived here, and then here, and then here, and then here, and then here. By collecting multiple observations in space, we can create what we call a synthetic aperture that lets us figure out what direction the radar wave was coming from. So the first step in generating a radar image is this process that we call SAR focusing. This is an image that we collected in central Antarctica. It's unfocused. You can see that there are all of these kind of blurry features in the bed. And so the first thing we do is we focus the image by this SAR focusing algorithm. It gives us a nice, essentially true cross-section of the glacier system. I'm just going to skip over some of this for a second. We'll come back to it if there's time. So we collected radar data in West Antarctica with this goal of studying what is the material underneath Thwaites. Oops. There were a team of 20-some geophysicists who I traveled with. This is a photo of our team on GHOST at a place called Waste Divide. Waste Divide is in central West Antarctica. It was the location of an ice core that was collected in 2007, from 2007 to 2011. And it has essentially become the, transit hub, gas station, staging area for West Antarctica, because they had put in a bunch of infrastructure there to support the ice coring project. And so in order to get to Thwaites Glacier, which is at the margin of the continent, we all traveled through Waste Divide, eventually out to our final field camp. So this was us, a wonderful team of folks from the US, the UK, and Germany. They were all of the different scientific organizations were represented on that project. This is me, if you couldn't tell. So, to give you a sense of what it's like to collect data in Antarctica, this is just a snapshot from my field book. I was there for 12 weeks. we were not collecting data for 12 weeks. In fact, it took us almost 6 weeks or more to get to where we were trying to go. So it's a logistically intensive process to get to Thwaites Glacier. To give you a sense for how one gets anywhere in Antarctica, I was coming from western or central Massachusetts here, and the first step in going to Antarctica is actually to go to Christchurch, New Zealand. So for me, that was 4 flights around the globe to get to New Zealand, which is the closest point, the closest landmass to the main U.S. base in Antarctica, McMurdo Station. And if any of you have been to Christchurch, this is the view as you're walking out the Christchurch airport. If you look to the left, you'll often see a lot of U.S. military craft. You can see right there, that's a C-17, a cargo military jet. Because the main U.S. Antarctic program is really based out of the Christchurch airport. This big shed here is what you see right as you leave the airport. Across the street is what's called the Clothing Distribution Center, where they give you all of your extreme cold weather gear that you'll use in the field. So when you arrive in Christchurch, you go to the Clothing Distribution Center. You've in advance told them kind of your size. They will have pre-packed 1 or 2 of these orange bags for you of all of the cold weather gear. You try it on, make sure it fits, and then you end up putting all of your equipment, your personal cargo, and your extreme cold weather gear into the cargo to travel down to the ice. So you go through customs just like you would leaving any other country. This is the security line. After you spend a few days in New Zealand, kind of preparing for your trip, you take a bus across the street from the Clothing Distribution Center, and you board one of these military craft, these ski-equipped military craft, to fly across the Southern Ocean to Antarctica. So this is us boarding actually what is an Italian LC-130 with some of our cargo there, which is what we flew from Christchurch down to Antarctica. It's a long flight, and it's, depending on what kind of plane you're on, it's fairly uncomfortable. It can be as long as 8 hours. But as you approach the continent, you get these beautiful views of the ice sheet. This video is a little bit fuzzy out the one tiny window of the C-130, but after 8 hours, you land on the ice, and you're in McMurdo, the largest base in Antarctica and the largest U.S. base. It's in an incredibly beautiful location because it's essentially where early Antarctic explorers landed. In fact, there are a lot of preserved huts from the early exploration of Scott and Amundsen in and around the McMurdo Station. So this is what McMurdo looks like. It has kind of a funny feeling of a cross between a mining town and a college campus. It's a very unique place. At its peak population during the summer, it has a population of about 1,000, which is big. Only probably 10 to 15% of those people are scientists. And the rest are the folks who support the scientists, who manage the programs, who manage fuel and cargo, and the Air National Guard, who manages transportation around the continent. It sits right under a large active volcano, Mount Erebus, which is an incredibly beautiful place. I think there's nowhere quite like it in the world. At McMurdo, we do our instrument setup and testing. So this was the radar that we were operating on Thwaites. It's a radar that is operated on the ground, dragged behind a snowmobile. This is me assembling the antenna fairing here for the system. These are the radar electronics that we were working through to make sure everything was wired up correctly before we mounted it onto the antenna. And we go through our first bit of testing of the instrument when we're in Antarctica. This is muted, so you can't hear whatever crazy things I'm saying. But this is me kind of describing our setup and testing out of McMurdo. We have 2 radar systems all mounted on the same chassis right here that we set up and tested at the airfield outside McMurdo. It's about 2 miles outside of town where the planes take off and land. Here we're actually sitting on the ice shelf. So we're on, I don't know, 10 meters or so of ice, but the roads out here cross the sea ice, which is only, 2 meters thick or so, 1 to 2 meters thick at this location. So this was our radar. We tested it driving around on the sea ice on McMurdo, and I put this in just to show you what a beautiful day and what a not so beautiful day look like in Antarctica. When it's beautiful, the skies are blue, it's cold, 10 degrees Fahrenheit, 15 degrees Fahrenheit at McMurdo, which is coastal, one of the warmest places where we were. But there are lots of days where it's snowy, overcast, where if it weren't for the fact that the terrain was rocky around McMurdo, we wouldn't be able to see much of anything. I also like to point out that there's a lot of science that takes place in Antarctica that is not glaciology. There are lots of reasons for that. It's a really unique position in the Earth system. It's extremely cold and extremely dry. So for scientists who want to see out to space, who want, like if you operate a radio telescope, water vapor in the atmosphere blocks your ability to see the light from space. And so there are folks who really like to study cosmological phenomenon, high energy physics from Antarctica. And one of the ways they do that is from these balloon platforms. So I mentioned that there's this westerly wind in Antarctica. Well, trapped inside that westerly wind is the polar air. And so balloons that go up to high atmosphere are trapped over the Antarctic continent. It's as close as you can get to a satellite from the terrestrial environment. So lots of physicists work in what we call the long duration ballooning facility, which is just outside McMurdo. For a while, these were the tallest buildings on skis on Earth. And in them, this is an example of a radio telescope that would be suspended from a balloon that they send up to circulate around Antarctica to study the origins of the universe. So there's all kinds of science taking place in McMurdo. This is also me. When we're there, they send us out to test our equipment to make sure that our tents and things are working, we have all the pieces we need that we can survive a night out on the ice. So this was our first setup and testing of our camp equipment that we would be using when we actually arrived at Thwaites Glacier. Because we were operating in a really remote camp. It was just 9 of us, ultimately, that were out in central West Antarctica, cooking for ourselves, living in tents, sleeping on the ground. I realized after about 6 weeks that I may be too old to sleep on the ground for 50 days at a time. When I was younger, it didn't seem to bother me, but now all of a sudden it does. So from McMurdo, once we've got all of our instruments tested and set up, we fly again from on a military craft out to that place called Waste Divide, which is here in central West Antarctica. And so I thought I would just show a brief video of what Waste Divide camp is like. Again, we go out to the airfield. We board one of these military LC-130s, these ski-equipped cargo planes, actually operated by the New York Air National Guard. And we take off from the ice runway. We travel out to our location, about a 3-hour flight, 3.5-hour flight, and we again land on the snow in the middle of the ice sheet. And so here, it's totally remote. Waste Divide is a pretty well-established camp. When you land, you walk all of your personal cargo out to snowmobiles so they can drag it over to where we'll eventually set up our tents. This is what they call Tent City. There were probably 40 or so people at Waste Divide when we were there. I'm walking out to my tent that we had set up. This is that orange-looking one. Kind of in the middle was my tent at Waste Divide. And here it's quite cold, probably minus 10 or 15 daily Fahrenheit. And this is me inside the tent. We sleep in groups of 2 or groups of 3 inside the tent, and it's 24-hour sunlight, windy, loud, and intense. So it's a very unique environment. You have to. In fact, the cold doesn't actually bother me anymore. It's the 24-hour sunlight. It's very hard to sleep when it's 24-hour sunlight. But this is driving through Waste Divide, where there's infrastructure for heavy machinery to deal with our cargo. This long building that we're approaching is the galley, where there are 2 cooks who prepared food for us. There were tents where we could clean up, store our toiletries, and tents where we would do science, where when I was waiting for a plane to come, I was working on my laptop. Just another example. On a nice sunny day, this is what it looks like. 12 hours later, it looks like this, where you have really no surface definition. You can't see any of the topography. It is truly unique being in these flat light conditions out in West Antarctica. So from there, we load up onto these very small Twin Otter aircraft. This is us. We're about to load that snowmobile onto the plane with all of our cargo. And then the plane will fly us eventually down to Thwaites Glacier, which is where we operated. So this is a relatively short flight, like a 2-hour flight. But the plane can only carry a couple thousand pounds, so it ferried us to and from Thwaites. This was operated by the British Antarctic Survey, so we had British pilots and British crew, which they were great. They did a wonderful job of getting us there. But again, these are small ski-equipped planes. So we fly all of our cargo out to our final destination. And I think in a moment you'll see where we landed. I was one of the last folks to go from Waste Divide to Thwaites. We landed at the surface and we set up our first camp where it was just the small number of geophysicists who we traveled with. And again, as I mentioned, we're cooking for ourselves and kind of making water, melting snow to make water for daily life out on the ice sheet. So, I forget, I think this video does show a brief view of camp down at Lower Thwaites. So this is now right out in the area, right in the middle of that bright red splotch where West Antarctica is losing mass. And our first, what actually felt like an evening there was clouds that kind of blocked out the sun. It was really a beautiful location. Still relatively cold, but now it was just our camp, our little small camp, subsisting out on the ice sheet. So over our period of time where we were at Thwaites, we collected a bunch of data. It was an integrated geophysical experiment. So there was our team, which was collecting radar data. There were people who were collecting seismic data, so acoustic wave imaging of the subsurface. There were people doing experiments using something called magnetotellurics, which measure the deep earth conductivity. But we tried to span as much of the glacier as we could to sample as many of the subsurface properties and kind of flow regimes as we could to try and tease apart why might the glacier experience high stresses in some places and low stresses in others, or be flowing fast in some places and slow in others, to really try and evaluate what we can see from space now from the perspective of process, what is playing out underneath the glacier that enables the ice to flow the way that we see it flowing. So when the instrument was working, this is what my experience was mostly like. We would drive snowmobiles over the surface of the ice with the radar operating. It would send out pulses of light, 10,000 pulses per second, measuring the subsurface, collecting all of those traces so we could map out both the structure of the glacier and what kind of materials, the electrical properties of whatever it's sitting on. And our instrument is a research grade instrument, which means that it's experimental and breaks all the time. So when it was working happily, we're dragging it around like this. But realistically, I spent a lot of time standing in front of it at a laptop, trying to figure out what the instrument was measuring, why things may have been going wrong, and then eventually opening it up and performing surgery on the interior of the electronics, which is quite rough when it's 20 below and windy and snow is getting everywhere. But yeah, my Antarctic experience is primarily building the instrument, repairing the instrument, diagnosing problems with the instrument as we drag it over the surface of West Antarctica. So in the end, we collected several hundred kilometers of radar data over some really interesting features on Thwaites Glacier, and the processing has basically just begun. So now our goal is to try and make sense of what we observed, see if we can understand what's going on in the subglacial hydrology, where water is, where it isn't, and why. See if we can map out aspects of the ice itself, where it's warm, where it's cold, what its crystal structure is, and answer questions about the materials that sit underneath the ice, where we think it's water versus sediment versus crystalline bedrock. So that is kind of my overview of the Antarctic field season. I'm happy to talk about radar data broadly, what other data we collected in Antarctica, any other logistics questions, anything that might be interesting to you all. Thank you very much.
Thank you so much, Dr. Holschuh. The floor is open for questions. Yes, Dr. Daniel.
Nick, thanks a lot for sharing. I think very interesting experience that you had. First question is I thought radar is airplane equipment. So what's the reason you only do it on the ground, not through the airplane?
So it can be done either from the air or on the ground. And there are some logistical advantages of each of those things. When you do it from a plane, you can obviously increase your coverage. Planes travel much more quickly than I can from a snowmobile on the ground. And it's also a very stable platform from the air. But it turns out there are actually some negatives for the imaging quality when you're from the air versus on the ground. You can, because you're moving more slowly, you can actually capture features that are dipping more steeply in the subsurface. There are some things that are hard to see, hard to focus in the image if you're moving very quickly. You can also do things like target very specific locations and reoccupy very specific locations. So one of the things that we were doing was collecting time-lapse measurements of the glacier. So a radar profile at one location in 2022, and then that same radar profile in 2023 to try and measure subsurface change. And really precisely redriving the same line is much easier to do than very precisely reflying the same line. And so there are some logistical advantages from operating from the ground versus operating from the air. So the specific components of our experiment were tailored around the advantages of these ground-based systems. But you're absolutely right that airborne radar is one of the ways that we've gotten really broad coverage over Antarctica and Greenland.
Thank you.
You're welcome.
Maybe I'll jump in. Really cool talk. I think the context was really helpful, and every time I see some of these visits to the field sites, it just makes a lot of sense connecting the dots with the data we see in the site. So I have a couple of questions, but let me start with one, where you talked about the radargrams that you collect and subsurface hydrology that you want to study. I'm wondering if you can connect an example back from the radargram to some of the context you laid back in the beginning, like what do you expect to see, or what would you like to see in the radargrams that helps you understand the impact of West Antarctica?
So it's a really great question, and I'm probably going to give you what is an unsatisfying answer because I think I could talk about this for an entire semester-long course. So there are a couple of ways that we might identify heterogeneity in materials from radar data. One way is just from the character of the reflection itself. So water is electrically different from rock, and so the brightness of the reflection at the base of a glacier should, in theory, change if there's a subglacial lake where there's a thick water column versus a very dry crystalline bedrock. That actually proves to be kind of hard to uniquely identify contrast in material properties because there are multiple factors that dictate the brightness of the reflection. Some that are defined by the electrical properties of the interface, some that are defined by the electrical properties of the ice itself. But in theory, one way that we should be able to identify water versus not water is by simply looking at the brightness of the reflection. But I think more in line with your question is how might this affect ice flow, and what do we see in the radar data that will help us evaluate how it affects ice flow? And there are a couple of different ways that we might answer that question. One is by looking at the morphology of the layers within the ice sheet itself. So in general, snow that accumulates on the surface of the glacier falls as what is kind of flat-lying strata. You might expect, because the surface of the glacier is relatively flat, that the layering within the glacier, especially in these fast-flowing areas, should also be relatively flat. But as the ice deforms and flows over this heterogeneous substrate, there may be areas where the ice is compressing or extending that causes those layers to buckle. And so by thinking about the geometry of the end glacial layers, we may get some information about the history of deformation within the glacier itself. There's also this question of time-lapse measurements. So we can go and look at layering within the ice sheet. We can measure it in 2022 and in 2023, and we can see how the very precise position of those layers has changed in time. And as those layers thin or advect through the system, it tells us something about how the ice is flowing in the subsurface. So we have really great satellite measurements of glacier flow, but only measured at the surface. We know how fast the surface of the ice sheet is moving. That translates to some motion in the subsurface, but we don't have a unique observational constraint that helps us convert measured surface velocities to measured velocities at the bottom of the glacier. But by measuring deformation through the ice column, using these time-lapse radar measurements, we might actually be able to close the loop between surface velocities and basal velocities. And so looking for heterogeneity in the pattern of thinning within the glacier might tell us about some places where the bed is very strong and is very actively resisting the flow of ice versus where the bed is very weak. That we've also seen in the really high resolution morphology of the bed. So that interface between ice and rock, we see that there are qualitative differences in the morphology of that contact layer, where we think there's crystalline bedrock and where we think there's disaggregated till or weak material. And so we can start to map out in detail the geometry of that interface, and it might actually tell us something about heterogeneity and material properties, which then can feed back into an ice sheet model that makes projections of future sea level rise. So there's geometric information both about the basal interface and the end glacial layers. There is what I would call radiometric information about the brightness of the reflections. And I would say those are the two primary ways that we might use radar data to diagnose variation in subsurface properties.
Very cool. If you are offering that course, I'll audit that. It seems like a lot of good information that you need to understand. And just to close the loop on something, a lot of connections to the ice layer annotations, I think, right? I mean, to the project that we have going on here, the ice layer annotation. If you can do that well, then it can help several of these questions that you're talking about. Right?
Yeah, I think that the end glacial stratigraphy, the layering within the ice sheet, is an incredible resource in these radar data that has been underutilized. And one of the reasons it's underutilized is because it is hard to extract quantitative information from these two-dimensional qualitative images. And so in some places in East Antarctica, we'd love to trace layers to figure out the detailed age structure of the ice sheet. Here, traced layers within West Antarctica could probably tell us a lot about the dynamics and flow history of Thwaites Glacier. And so the auto-annotation project that we have within iHARP, which is really trying to digitize all of these layers within the ice sheet, really could do a lot to advance our understanding of ice flow here in this very complicated region.
Great. Thank you so much. No, deep other questions.
You're welcome.
Sudeep?
Yeah. Hi, Nick. Nice talk. Thanks. So I have a question. You mentioned that the melting of the glacier can be connected to the sea level, sea ice retreat in the nearby region, right? So is there any study that looked at like what's causing that? Like, is that a mechanical force by wind or wave, or is it purely thermal, or which of the features are more important? Is it more because of the mechanical forces like wind and wave, or is because of the thermal or oceanic flux, things like that? So do you know any study that worked on that?
It's a good question. So I'm not myself a sea ice expert, but I do know that there are lots of folks who look at Antarctic sea ice variability over the observational record to kind of understand the climate system and also understand how it might change things like buttressing in and around these marine terminating glaciers. I think sea ice probably plays a much more significant role in restraining ice flow in Greenland, where there are narrow fjords that can be choked with sea ice. And so the mechanical strength of that sea ice outboard of the ice sheet is much higher. But I think there are active, there are lots of interesting projects working on Antarctic sea ice variability and what it means for wind and the opening of polynyas that act as sea ice factories on the margins of the ice sheets, what it means for thermal forcing. But I think about sea ice in its role in changing the buoyancy forcing of the ocean. Where you have sea ice, you have brine rejection, which causes winter overturning, which actually brings heat back up to the surface of the ocean, which can be recycled to the atmosphere. And so where you have lots of sea ice production, you can actually cool that circumpolar deep water in a way that it doesn't get cooled when you don't have that buoyancy-driven flux. And so that's a long way of saying that people definitely study this. I am not an expert. And so if you're interested, I could probably help point you to some papers that look at Antarctic sea ice change over the observational record.
Yeah, thanks. Yeah, I guess like, so I was thinking like when you go down deep down the layers, not at the surface, maybe do you think like we can differentiate the effects of mechanical forcing versus thermal forcing, looking deep down the surface, looking at the annotation layers from the data, radar data? Is that possible to like distinguish what's causing it? Just a question, I'm not sure.
Yeah, so I have to think a little bit more about your question. So the radar imagery that I present are all collected over land ice, not over sea ice. And so it's all a record of the interior of the ice sheet. I think that it's what drives buttressing changes at the margin wouldn't be distinguishable within the stratigraphy in the interior. All the interior of the ice sheet knows is that there's been a stress change. And so you could have a marginal stress change because you have increased ocean heat content that melts the ice shelf where it goes afloat. You could have changes in marginal stresses associated with buttressing, mechanical strength of sea ice that's restricting ice flow. And there would be no way to tell the difference between those two things from the interior response.
Okay.
I expect, though, for Thwaites, very little of its history is really mechanically dependent on sea ice. It's likely much more influenced by changes in ocean heat content in and around the grounding line.
Oh, that's interesting. Yeah. Thanks.
You're welcome.
Any other questions? We have some acknowledgements from Matthew and Ali in the chat. Yeah. Any other questions?
Happy to ask one more question if you have time. So it's very interesting. We were showing in West Antarctica is melting so much faster than the rest of Antarctica. Maybe I already explained, but what's the reasons behind which, from maybe physics perspective, what can you summarize the reasons?
Sure. So some of it has to do with ocean access and the transport of that warm circumpolar deep water. So where does warm water actually make it up onto the continental shelf and abut glacier systems? There are some places in Antarctica where the ice shelves are not receiving warm ocean water, and so that forcing isn't experienced at the margins. And some of that is because there's extremely cold surface Antarctic surface waters there that crowd out the deep circumpolar deep water. Some of it is because there's glacial meltwater. As ice melts, it produces the coldest possible fresh water, right? Because you're going through a phase transition, and so what's left behind, the product of melting, is extremely cold water. And so areas that are downstream of high amounts of melt receive cold surface meltwater from the glacier that also inhibits additional melt. And so there are geometric relationships around the continent where some places are receiving glacial meltwater that actually insulates them from further melt. Some places don't receive any circumpolar deep water, which insulates them from melt. But really what makes West Antarctica really unique is the geometry of the ice sheet itself. And so it is what we call a marine ice sheet, which is thin at its margins, sitting on the seafloor, and thick in the interior, with a retrograde bed slope that facilitates that marine ice sheet instability I described, where a little bit of melting leads to thinning and acceleration, and thinning and acceleration, and thinning and acceleration. And so East Antarctica, if you were to pull all the ice off the East Antarctic ice sheet, what you would see is a relatively high elevation continental crust. And there would be a continent there, and it would look extremely mountainous, very rugged. And as a result, what that means is that the ice there is sitting on slopes that kind of slope out towards the ocean. So as the ice melts, it actually retreats into a more stable configuration. Absent ocean forcing, we might expect that the Antarctic ice sheet should be growing, because atmospheric temperatures have gone up. They just haven't gone up enough to induce melt. And so as the air gets warmer, the carrying capacity for water vapor goes up, and we might expect higher water vapor transport from the ocean onto the continent, where it precipitates as snow. And so when you look across East Antarctica, much of East Antarctica is actually gaining mass. And it's gaining mass because there's higher precipitation and none of this ocean-driven melt going on. West Antarctica, by contrast, is also experiencing higher precipitation, but the ocean is dominating. And so the ocean-driven melt outcompetes increased precipitation to lead to a net mass loss. So it's a combination of where the ocean can actually act on the continent and how the interior of the ice sheet responds to that marginal forcing.
Okay, thanks. But if summarized to be one sentence, it would be elevation of the ice patch below the sea, below the ice sheet. That's a big difference between this continent. That's the one major reason why that behaves so differently between the west and east.
It is. Yep.
Thank you.
Question?
Great. I think there'll definitely be follow-ups, Nick, when we have our other meetings. I'm sure we'll come back to some of the questions.
I have a question. I have a questions to Dr. Nick.
Sure.
Yes, you are using the radar, ground penetrating radar to collect the data, right? So
Yes.
So there are a lot of radars available. There is any advantage of this ground penetrating radar, like millimeter? If I talk about, there are a lot of radar named millimeter wave, microwave, and others. And what is the specialty of the ground penetrating radar here?
So these specific radar are designed with a couple of things in mind. You have to be in the frequency range where ice has low conductivity, where the imaginary part of the permittivity is low. Because at some frequencies, the ice is absorptive. And so you typically want to be between 1 megahertz and 10 gigahertz is the frequency range that you can actually see through the ice sheet. The radar that I showed you is a multi-channel radar system. So it has an array that is 8 elements wide. There are 8 individual receive channels that are listening. And that allows you to do direction of arrival analysis for the incoming wave. So you can now, instead of just mapping right below your instrument, you can map to the left and map to the right in the same way that multi-beam sonar and other technologies have been used to map kind of a swath of the subsurface. They are designed with a transmit pulse that allows you to identify reflections with a particular resolution in the subsurface, but still transmit with high enough power that you can see through 3 kilometers of ice. Because even though ice is non-conductive, it's still not a perfectly lossless material. So these radars have a very tight, what we would call a link budget, a very tight power budget to make sure that there's enough energy transmitted that we can see through 3 or 4 kilometers of ice. Especially given the fact that the electrical contrasts that are generating the reflection are very weak. And so less than, probably on the order of 1% or less of the received power is actually reflected. So to actually measure that power, you need to have really optimized your system to get energy down to your target. So there's a ton of effort that goes into engineering these things to make them optimal for looking through ice sheets.
Just one quick question, Dr. Nick. Like, as per the physics rule, we know that radar first emit a signal, by the transmitter, and the receiver should get the signal back from the reflected object, right? So when the radar is moving, it is getting enough time to get the reflected signal. There is any time ratio you are maintaining, like on, because it is moving, right?
So typically when we think about radar data, we think about fast time that involves the propagation of the radio wave and slow time, which involves the propagation of the instrument in space. Because the speed of light is 168 million meters per second in ice. And so to measure one of these pulses, you're measuring, let's see, 2 or 3 microseconds of signal, basically. So 10 to the minus sixth is the order of magnitude for the duration of one of these time series measuring the reflected wave. And in that time, the instrument has hardly moved at all, because we're moving at order, I don't know, 10 kilometers an hour. So, so the time it takes to listen to the reflections is minuscule compared to the displacement of the instrument.
Oh, got it. You are always maintaining a uniform velocity as the
That's right.
As the physics law, so that there is no disruption. But
that's right. Yeah.
But my feeling is, like, depending on the velocity of the vehicles, like the radar velocity, it may be the imaging may be, the quality may be a little bit. I think it finds some other things. It may be right.
I mean, the geometry of our targets in the subsurface, they're huge compared to our speed.
Yes.
So, I mean, it is an interesting question, but I am probably at the limit of my radar engineering knowledge at this point.
Sorry, I have not so much.
Malloy, maybe what if there's any other final questions we can see. I think we're getting close to time as well, Josephine. I don't know if you have anything.
Yes. Okay. Sir. Thank you.
Thank you.
Thank you so much, Dr. Holschuh. It was very, very interesting, and thank you for sharing your experience and your notes from the field. And thank you all for joining today's talk. And any follow-up questions, please feel free to direct them to Dr. Holschuh. Absolutely.
Thank you very much.
I will enjoy the rest of your evening.
Thank you.
Okay.